How you doing? I'm Mr. Rose, and today we're going to talk to you about electric charge and electric field. Now, this is a large informational session. It may go a little long, so I want you to know that, but this is to make sure we're all on the same page and everyone knows where we're going. So, first thing is electric charge and electric field is kind of a two for one. In other words, it's kind of two chapters smashed together to form one thing. Now, we do know a little bit about field theory. In fact, we've learned a lot about gravitational fields. And we learned that the gravitational field is related to a mass or an object. Well, we have a lot of similarities, I should say, that we're going to speak of. So to talk about things that we know, Newtonian mechanics. Well, Newtonian mechanics have to do with mass. We know that every mass has some gravitational field. And that gravitational field shows us the direction of which masses are going to be attracted. For example, if I can imagine the Earth as a large giant sphere with these field lines all going towards the Earth. How do I know all the field lines go towards the Earth? Very complicated experiment. Here I have a mass. If I let this mass go, it will fall right off the camera straight down to the Earth in that exact direction that my gravitational field line was going. Well, electricity and magnetism have similar things. Mass is a property of matter. Well, so is charge. Charge is some property of matter. In other words, every object, all matter is made up of different charges. Just like mass, all masses have some gravitational force with it. All charges also have a force that we call the electrostatic force. Now, one of the big differences between a gravitational field and electromagnetic or an E field is that the E field shows an attraction or a repulsion, and we're going to get into that, but not all electric fields show attraction. What an electric field does is show a definition that is very specific based on some positive test charge. We're going to talk about that in a little while. So, Newtonian mechanics, we do add some other physicists into the mix, obviously, like Kepler and Galileo, but it surrounds a whole lot about Isaac Newton. Electrofield or electromagnetism has a whole slew of contributors, basically starting with Faraday and ending with Maxwell and some people in between. So things that we do need to know about our field theory, at least to start, is that an electric charge, all objects have these electric charges. Doesn't even matter if something is electrically neutral. They're made up of all of these charges. And charges interact with each other by applying forces to them. So masses interact with each other. We know every mass has some gravitational force that goes with it. There's an interaction between them. But most masses are so small that it doesn't actually matter. We can't really account for that. Well, charges also interact with each other. We know that opposite charges tend to attract. We know that like charges tend to repel. And then what I have written down here, we can only test whether two objects are charged if I bring them near each other and I can measure some repulsive force. And the reason for that is opposite charges repel, all neutral objects will attract to any charged object. And that happens because of something that's called induction, charging via induction, where I don't have to transfer electrons back and forth, but I can influence some charge and influence some attraction. So we can really only test to see whether two objects are charged is if they repel for each other. We also know that charges, just like mass, is always conserved. So, and I have this local word here because remember, charges are conserved, but because electrons and charges are so small, if they're moving fast enough, there's a lot of things that go on. We can have some quantum mechanical effects, and we're not going to talk about any of that here today. So I want to say that charge is conserved, but it's a local phenomenon. Well, we know that objects are really broken down into two types. We have conductors and insulators. Now, there are more than I have written there, and more. There are more than just conductors and insulators. So a couple things. Firstly, we don't like the word insulator. We classify conductors and insulators, or like I said, we just don't really like that word insulator, as conductors and non-conductors. Now, conductors and non-conductors are classified by the ability of charges to move through them freely. So a non-conductor, or what we traditionally call insulators, means that electrons or electric charges are not able to pass around through those things very freely. Now, there do exist things that are semiconductors and superconductors. A semiconductor is something that is made up of like a germanium or a silicon, and that falls in between a true conductor and a true insulator. And then there are these superconductors. Superconductors are something that have virtually no resistance to them. Both of those objects are outside of the scope of what we're going to be studying this year. Now, aside from conductors and insulators, how can we describe the way charges transfer back and forth? The way we do that is something that's called the triboelectric series. Now, I invite you to use a search engine to look up the triboelectric series, but in principle, if I take a balloon and I rub that balloon on my head, we know that there are charges that are either on the balloon or maybe charges from my head. We're not really sure. Well, the triboelectric series is what defines that. And it is an order of which objects will either give electrons away or take electrons. So when I take that balloon and I rub that balloon on my head, I know that me and my hair are more of an electron donor than the balloon would be. So I'm giving some of my electrons to that balloon. I take the balloon and I shove that balloon on the wall. The balloon charges the wall via an induction, like I said before. I charge that balloon via friction, and I transfer electrons from my head to the balloon. So I invite you to look up the triboelectric series so you can see a little bit more about that. I also want to point out that you should read section 21.2 at the minimum in your textbook, and that text is University Physics, for a complete understanding of Coulomb's law. So what is Coulomb's law? Coulomb's law is the law that shows the electrostatic force between different charged particles. So I have Coulomb's law written here as F equals K Q1 Q2 divided by R squared with my little r hat. And you can see this looks eerily familiar to Newton's universal law of gravitation, and they do have a lot of similarities. Things of note, it is a vector, so I have my vector notation there, and I need my r hat to make sure it is in proper vector form. And K is an electrostatic constant. Now, very similar to Newton's universal law of gravitation, this was something that we could find experimentally, and it was something that was proved experimentally over and over and over again. K is our electrostatic constant, and K is 8.99 times 10 to the 9th Newton meter squared per Coulomb squared, and that is just our constant that makes everything work. Now, there's also some background information here. Now, Newton's laws, we know, do fall apart at some points. Now, the electrostatic force, or Coulomb's law, actually doesn't. No matter what we throw at Coulomb's law, it always seems to hold true. Whether that is the electric force that's going on inside of a nucleus, whether that's the electric force or interactions between protons and electrons, or molecules that are being held together by other forces. We know there's something called the strong force and a weak force. The strong force is responsible for holding molecules together. Well, all of that being said, we can still calculate the interaction between charges. Another thing we want to say is that Coulomb's law only deals with two charges at a time. So what does that mean if I have three charges, four charges, some system of uniform distribution of charge? Well, we know Coulomb's law, I'm going to skip down here for a moment, does obey the law of superposition. Now, there's no actual proof for this. It's more of an experimental thing. I can't look at this formula and say, oh, that happens to be. No, it's just we know it's a force, and forces obey the law of superposition. Coulomb's law obeys the law of superposition. So we know that if I have, say, a system of charges, I can find the force between 1 and 2, and 1 and 3, and 1 and 4, and 2 and 3, and 2 and 4. Add all those forces up in the proper vector forms. That might mean we need to use a little bit of trig and or some calculus, and we can find the net force acting on that object. So Newton's laws do obey the law of superposition. The Coulomb is our unit for charge, and a Coulomb is actually derived from current electricity, from the definition of an amp, which we'll get to in a later chapter. But an current, or an amp, is defined as our change in charge per unit time. So 1 Coulomb is actually equal to 1 amp second. Next thing of note is this K is my electrostatic constant. We're not going to use that all of the time. In fact, most of the time, we're going to use 1 over 4 pi epsilon naught. Now, obviously, they're equivalent because, look, I'm telling you K is equal to 1 over 4 pi epsilon naught. But epsilon naught is something different. We're going to use this for a couple of reasons. One, historically, this is more accurate, or not more accurate, but what we tend to use. Second, epsilon naught is something that's called the permittivity of free space, or what it is the resistance to form an electric field in that space. So we're going to talk about that as we go forward. Now, excuse me. To continue, some more things or some things that we want to make sure that we remember is we want to remember things like the shell theorem. Now, we talked about the shell theorem with Newton's universal law of gravitation. What exactly is the shell theorem? Well, the shell theorem was if I imagine the Earth as a big sphere, because it's pretty much a big sphere, if I start digging down into the Earth, underneath some, can't see that, underneath some part of my layers of the Earth, I'm going to ignore all that stuff that's above. Same thing is going to happen here. What the shell theorem is, if I have some charge above a uniformly charged distribution, I'm going to assume a couple things. One, that all of my charge is designated at the center of that uniform charge down here. Second, that if I bring my charge, say, inside that hollow sphere, the charges that are outside are not going to have any effect on my test charge. So in other words, the shell theorem for electricity and magnetism is going to say that if I have some positive test charge inside of a shell of charge, that there's no net electric force due to the charge distribution that's uniform above it. I hope that makes sense to you. The second thing we want to talk about is uniform distribution along some spherical conductor. What that means is if I have a spherical conductor and I place one electron on the top or one charge on the top, obviously it's just going to stay there. If I put two right next to each other, they're going to separate to the other sides. If I put three, they're going to separate. If I put 4, 5, 6, 7, they're always going to evenly distribute, continually to distribute around that uniform shell. This way it shows that there's a uniform distribution. Well, why does that happen? That happens because I'm putting all of these like charges near it, and we know like charges want to repel. They want to get as far away from each other as possible. We're talking about a conducting sphere. A conductor, something that's going to allow those charges to flow freely over them. So they're going to try and separate uniformly as much as they possibly can. That arrangement is easily predictable. A couple more things to continue to know. We have to know that charge is quantized. Even in things that are continuous, have a continuous distribution, like say a fluid like air, they're a continuous distribution of air molecules, and air molecules are made up of protons, electrons, and neutrons, and the protons and electrons all have specific sizes, and that size is 1.6 times 10 to the negative 19th. I can't have any non-integer number of charges, and this is the value of one charge. So if I wanted to know the total charge in an object, Q, I would need to know the number of elementary charges. Now, I know I have this written as a negative as an electron, but we know electrons and protons have to be the same size, or the same charge, not the same size. So this could easily be a positive number as well. I know the total charge is however many I have times that elementary charge. How big is that? Well, it's actually very, very small. For example, a regular 100-watt light bulb is essentially pulling 10 to the 19th charges per second. So it is a really, really, really small number. That is a bunch of stuff on electric charges and electric forces. Well, that leaves us with an electric field. Now, electric fields are a little bit of a strange concept. That brings us back to the concept of action at a distance. And we've done a lot of that with gravitation. The gravitational force is, in a sense, action at a distance. It is applying a force to an object without physically touching it. Now, even though we're comfortable with that, because we're very comfortable with gravitation, still, if I asked any of you, what do you think a force is? You're going to define it as a push or a pull. Then when I ask for an example, the example that almost comes out first is, well, what if I pushed that person? That is a physical thing. We don't think about the force of gravity pulling those objects down, that attractive force. That's not first on our head. So this does give us a little bit of an issue, which is why we created what we have called the gravitational field, or now the electric field. An electric field is the space that surrounds any charged particle. Now, you do have a lot of experience with fields before, aside from gravitation. We could say, hey, maybe you know what a temperature field is. Have I ever sat in front of a fire because I'm cold? Well, I have, perhaps you have. And we know as soon as I light that fire, I'm sitting there trying to warm up. And as I gradually stay there, it gets warmer and warmer and warmer. And I can take those temperatures and I can make a heat field with it. I can get further and further away. I can get a uniform heat distribution. Now, that's a scalar field. And an electric field is actually a vector field. So that does make it a little bit more complicated. But an electric field is really just a field of vectors. Well, what does that mean? An electric field is, as I said, the space that surrounds any charged particle, and we define its direction as the reaction of some positive test charge, and what it would do if I took this positive test charge and I placed it near this massive charge that's producing this field. So it is just something, electric fields are real, the electric field lines are something that we draw to make ourselves a little bit, to make it a little bit easier to understand what's going on with those. It is a measurement of the electrostatic force, how that electrostatic force is going to react in that field. I'm sorry, how that charge will react in that field. We know the electric field is some electrostatic force, like Coulomb's law, divided by an amount of charge. Our unit is a Newton per Coulomb. We can rearrange it, and we can say that a force is equal to some charge Q naught. That's the charge that that I'm testing, rather, in that electric field. One thing we need to know about this, however, is that even though I am measuring the electric field with that charge, with this Q, the electric field exists independently of that charge. So that's something that's very, very important. The electric field exists based on the arrangement of something else. I'm measuring that electric field with that charge. So that's something that's very important. We're going to sum things up. I had actually written that down already up here, that the electric field exists no matter what, independently of that test charge. And what are we going to do with that? Well, the electric field can do a couple of things. Well, let me move this more center. That would just make some sense. The electric field, we can calculate an electric field given any charge distribution. We can also calculate a force from that electric field. We can also calculate a force of the given electric field that exerts on some charged particle. All with, right now, just two simple equations. Coulomb's law and the electric field, E equals F over Q naught. So the last thing about these electric field lines, or the electric field lines are a visualization. If I don't have the lines, it doesn't mean the electric field doesn't exist. The electric field lines are there to help me understand the relationship that exists between charges and or charged particles. It shows the relationship between the electric field lines and the vectors that go with them. So if I have electric field lines that are all nice and straight, I know that my vectors are obviously going in those straight lines. They're pointing in the same direction. However, if I have some curved electric field lines, then I have a different direction at every point. So to figure out what that direction is, I'm going to take my electric field line. I have a little space right here. If I have an electric field line, say, that's going in that direction, my field vector will be any point tangent to that spot, just like I drew on the board. We've done a lot of that before, and it would make sense. These are just a sum of lots of little vectors drawn tip to tail that show that direction. So my direction at any distinct point has to be tangent to that line. Something else about electric field lines, when they are drawn, electric field lines are drawn proportionally to their strength. So if I have a lot of condensed electric field lines, I know there's a strong electric field there. If my electric field lines are drawn very spread out, I know there's a very weak electric field there. I also know that electric field lines are never allowed to cross, because remember, it's the direction that a positive test charge would go. So if I had a positive test charge going this way, it can't cross another field line because it would want to take that direction. To visualize this, because I know electric fields, you might be confused, and how do I visualize things like this? I invite you to use any search engine. I'm a big believer in Bing. I'm not a big believer in Bing. I use Google like the rest of the world. Google and or Bing, or maybe even use Yahoo, and look up electric field hockey. There's a simulation on a website that is called PhET. It's run by the University of Colorado, and there are different levels, of which the point is to get some positive test charge into a goal by setting up different charge distributions. It is a good way to waste time, and if you're a physics geek like me, it's a lot of fun. That's all I have for you today on all of this background. We're going to get to some practice soon. I invite you to please like, comment, or subscribe if you hung in there for the full 20 minutes. Thank you very much, and you'll see me next time.